Okay, good evening and welcome to the fifth week of the Introduction to Machine Learning course. We finished last week two lectures. The first was on curve fitting and the second one was linear regression using basis functions. Okay, we will continue on that topic today. Just as a reminder, what linear regression is about is you have given a set of input points which may be multidimensional. We want to produce an output that corresponds to them. There's a variety of applications for linear regression. And one example I've constantly given is that of an automobile driving, where the input is a very high multidimensional sensory input coming into the car, and the continuous valued output perhaps is the accelerator or the brake or the steering wheel and so on, right? Yeah. Another example I gave was about the search engine problem. Sometimes a problem doesn't look like a regression problem, but it's interesting how it can be converted into a regression problem. This search engine ranking is one of those. It doesn't seem to be a regression problem where we're trying to see how we can use machine learning to improve the performance of a search engine to give you more relevant results than what it's already giving by having people provide a data set for you, by coding the choice as good or bad or in between and so on. A value between say -1 and +1, a continuous value. And we take features from the query that you type in into the search box and features from the page that you're looking at. And those features should map into the correct sort of values. And so that we can learn how to map into a higher scoring values. So that's another example. So there are varieties of applications of linear regression. So we did that, and we said it's really a curve fitting problem. If it's just one output, it is some kind of an input output. So it's like a y versus x, except that the x can be multidimensional. And we saw that it's possible to replace that x by what's called as a basis function phi of x. Why the basis function phi of x is to reduce the complexity, the dimensionality from a very high dimensional space into something manageable, and also to find reasonably good solutions to the regression problem and so on. So we can use either x or a phi of x for the same thing. And we saw examples of linear regression formulated in terms of minimizing the sum squared error solution. Sum squared errors, and a solution can actually be expressed as a closed form expression, which says all you need to solve this problem is one line in NumPy or one of these kinds of tools, which simply takes the weight vector that you want to compute, the weights associated with each value of x. That's the weight vector, the solution vector. Machine learning problem is nothing but the inverse of the design matrix multiplied by the target vector. Target vector is all the outputs associated with all your examples that you have. And the design matrix, rows of it correspond to the n samples that you have, columns corresponding to the features or the components of the vector x or the components of the feature vector phi of x. As simple a solution as that, except that the particular design matrix, you need to invert that. It's the inverse of the design matrix rather than the design matrix itself. And that inverse may not exist. That we don't have a square matrix, an n by m matrix. The inverse doesn't exist. So we use a what's called is a Moore-Penrose pseudo inverse, which can convert it. For which we can take an inverse, and then we use that. And still there are problems with that solution as well, numerical type of solutions. It's not a common go-to solution to the problem. Instead of that, we use an iterative solution, which is a gradient descent solution. The classic go-to algorithm for machine learning is gradient descent. So that's so today we'll pick up on where we left off. It's kind of in the middle of that discussion of the closed form solution, and from the closed form solution we go to the solution based on gradient descent. So that's where we begin today. So let me at this point share the screen, and we will. So I'm going to open up the slide titled linear regression using basis functions. You would have noticed that it's already, I think I put it last week itself on UB Learns in the documents section, course document section. And I've already put the next lecture, which we'll touch upon today, is the gradient descent part of it, right? So that's, so if you want to follow where we are, I'm kind of following the structure of my lecture slides, which are publicly available. You got, some 15 or 20 chapters there on what's all the material on machine learning. We are right now in chapter 3. Chapter 3 is about linear regression. And we'll finish up miscellaneous parts of linear regression this week. Next week, we do classification. We begin with linear classification. And your first project is about linear classification. I believe you're doing logistic regression as the project. And I was just discussing with Mihir earlier today. I understand your due date is October the 7th for the first project, which is today is what, just this 28th. So that takes us into 9 or 10 days more from now, right? So which is on a Wednesday, due date on a Wednesday. I suppose it's the next week Wednesday must be the date. Anyway, you can check on that. We aren't changing that. So you're going to be, so we'll do linear regression wrap up today, and we will do linear classification next week, which kind of relates to your project also. Hopefully you're already getting a solution to the problem. We will talk about it more formally here. So that will become chapter 4, and then there are other topics in machine learning you'll see on the public site as to what else are we going to learn here. And after we finish supervised learning methods, we're going to do unsupervised learning methods and so on, and conclude with reinforcement learning at the end of the semester. So anyway, it's good to have an idea where this is all going. So first project is this one. Okay. All right, then I'm going to share a screen of today's lecture. Okay, hopefully it is seen in maximum size. If not, let me know. So we are on slide 40. Okay, so we covered 39 slides already on linear regression with basis functions. So we're kind of in the last quarter of this particular topic of linear regression using basis functions. And we've come to the point where the ML here doesn't stand for machine learning, it stands for maximum likelihood. It's kind of interesting that two of the most common abbreviations in this topic is ML is machine learning, ML is maximum likelihood. All right, here we are using maximum likelihood solution. So we said WML is the maximum likelihood solution for W, right? Which is actually machine learning solution for W as well. Is written in this peculiar way. There's a whole bunch of things going on here. Phi transpose phi to the inverse of times phi transpose times t, and all those phi things in the beginning phi transpose, phi inverse, and phi transpose. That is the Moore-Penrose inverse of the matrix phi, which is nothing but the design matrix, which is rows and columns arranged appropriately. So that is it. Now we call this a solution as a batch technique. In the sense, we take the entire training set in one go, and we simply say apply the Moore-Penrose inverse. And once you have got that, you just multiply it by the target vector and you got your solution. All right. That's a one-line solution to the entire regression problem. It's a batch technique, processing entire training set in one go. It is computationally expensive for large set data sets due to huge N times M design matrix. So you might have a large number of samples, you might have a large number of features. So the solution is to use a sequential algorithm where samples are presented one at a time or a mini batch at a time. So this one says you use all your samples together. It seems to make sense to use all of your data simultaneously. The other one says a sequential algorithm. You present it at one sample at a time and adjust your weights. Or you take a mini batch, a small number of samples. Take 16 samples at a time and adjust your weight. And we call that a stochastic gradient descent approach. So it's a gradient descent approach where we try and minimize the error by looking at the error function or a cost function or the loss function, more correctly said. And we try to find how to change the weight so that you are heading in the direction of doing better.
Professor,
So,
sorry to interrupt.
yeah, yeah.
Can you make your presentation go full screen?
You are not able to see. Okay, you know what I did? I think I did it locally. I did, full screen view. That is not good enough. So I need to do it into, view slideshow mode, which means I have to start all over. I was trying to be lazy here. I'll do slideshow mode, which means I have to rapidly go through 40 slides, which I was trying to avoid. I said, let me try full screen. All right. Better?
Yes, Professor.
Yeah, okay. So computational bottleneck. Machine learning is a really nice amalgamation of linear algebra, which you've seen quite a bit of it because of the way I'm teaching it to cover linear algebra a lot. There's also probability theory. I've kind of skipped on the probability theory a bit because I thought maybe it's some of it already, but you may want to look at my slides on probability theory. So it's a real nice mix of linear algebra, probability theory, calculus, as well as computational complexity. So the computational bottleneck, that's what they're saying. A recurring problem in machine learning is that large training sets are necessary for good generalization. Right? Generalization again means you're not overfitting, but you're generalizing to samples that are unseen, not seen. But large training sets are also computationally expensive. And stochastic gradient descent is an extension of gradient descent that offers a solution. Moreover, it's a method of generalization beyond the training set. This is kind of peculiar in machine learning, where we say, don't solve the problem exactly, because if you solve the problem exactly, you are going to be overfitting your solution. And in machine learning, we don't look for a best solution that fits your data exactly. We are saying loosen it a bit, loosen your solution a bit so that you can handle data you've not seen before. It's kind of interesting philosophy as to why machine learning is different from optimization. Because machine learning is about generalization, we say, generalization to samples that are not seen. Stochastic gradient descent brings in noise. When you adjust your weight vector to a small set of samples, it may be adjusting it in a noisy way, in that the sample is not representative of the population. It's like using just a few to make a decision. I was trying to look at the analogy, because we're in the election season. I guess we don't use stochastic methods here, because we take a sample of 1,000 people and ask them who are you going to vote for, right? That's how they release the polls. But what if we ask only 16 people and say, who are you going to vote for? You're going to get a pretty noisy estimate. They might all be 16 people from one rural area of New York State who might all have the same opinion. It's not representative of the urban and the rural and everything else. So you'll get an extremely noisy polling. But in machine learning, when we look at samples, we say that is actually good, getting a noisy polling, because you're going to show another set of samples, and so you're going to be eventually training on all the samples, but it says do mini batch at a time. That's going to give you some degree of generalization to your solution, rather than digesting all the data at one time. On the one hand, digesting all the data at one time is computationally expensive. On the other hand, it also gives you a solution which is less prone to overfitting on the data. Is that interesting? I don't know if they use stochastic methods in processing the polls that they do. Probably not, but in machine learning, that's what we do. Okay.
Professor, there's a question by Jonathan. Sorry to
Yeah.
interrupt.
Go
The
ahead,
question,
Jonathan. Yeah.
yeah. So the question is, what is the advantage of using gradient descent over a genetic algorithm? Wouldn't a genetic algorithm avoid issues of local minima? Is it an issue of efficiency?
Oh, wow. All right. This is a pretty informed question you're asking me. Informed in the sense you know about genetic algorithms, right? So that is another whole separate class of algorithms where we are trying to model, evolution, right? That's the kind of idea they use there, which is this is like a theory of evolution and so on, so that they apply that in genetic algorithms. For some reason, we don't use genetic algorithms as a mainstay of machine learning. All right, that's something interesting that you're asking. It's outside. You will not find genetic algorithms as a standard technique in machine learning, right? So it's kind of a totally different approach. You're asking a research question. What are the advantages, disadvantages of genetic algorithms versus machine learning algorithms based on gradient descent or stochastic gradient descent? That's an interesting question. I don't have a very good answer to that one. Maybe you can look at some insights. Supposing you want to solve a problem using genetic algorithm versus standard machine like linear regression, linear classification. Are there any advantages, disadvantages with that? Maybe the regularization issues are going to be there, computational issues are there. We are discussing truly well-tested and methods here. Genetics seems to be a slightly different style, and that's pertinent to a different approach, a different take on the problem. Okay, so I'm going to leave it at that. All right. Okay, any other question? Okay, back to our stochastic gradient descent. All right, SGD is the main workhorse of machine learning and deep learning. Right, this is the main workhorse. So let's not lose sight of this. Oh, okay, there's something else around. No, SGD is the main workhorse, at least today. Right, it's the main workhorse. So gradient is going to be in the form of an expectation. All right. So it says the gradient of log py is going to look at that equation in the box up there. It says beta some summation here. Whenever you get a summation, we say that's an expectation because you're summing over some quantity. In this case, summing over the number of samples here. And this is y minus theta transpose. That's after you take the gradient. It's y minus theta transpose of x. So y is the desired output, and x is the input, and theta is the vector of weights, and that has to be multiplied by x again. Where did you get that expression from? If you ask me that question, it is obtained by taking the derivative. You see that inverted delta here. This inverted delta stands for gradient, or the dy by dx, except it's the generalization into multi dimensions. And so, but the behavior is very similar to a univariate case. If x was a scalar, this would be y minus theta transpose x. And if you remember, sum squared error would be sum over all the samples of squared. When we take the derivative of that quantity, that 2, and there used to be another 1/2 here, that's gone. And you have to also multiply it by x, because there is an x term inside the power of 2. That's where that x came from. So this comes from calculus. What is the derivative of y minus x whole squared to the power of, to the, you're taking the derivative with respect to x here, all right? And there is also a beta parameter, which consists of the noise associated that we are adding. So all this derivation was in the previous slides. But anyway, there is an expression. It says in each step of SGD, we can sample a mini batch of examples. So instead of looking at all the samples M, we look at M prime, some smaller number, drawn uniformly from the training set. The reason they began to use M here rather than N was the number of samples, right? M is the number of so they're using a different terminology here than the number N. That's all it is. So drawn uniformly from the training set. Mini batch size M prime is typically chosen to be a small up to 100. And crucially, M prime is held fixed even if sample set is in billions. Okay. In machine learning, we might have very huge training sets. Even if it is very large, you keep it small. We may fit a training set with billions of examples using updates computed on only 100 examples. So this is one of the principles of stochastic gradient descent, where we decide to compute the derivative. And what are we going to do with this derivative? If you have forgotten, the derivative is going to be used in the gradient descent term, in a gradient descent expression, where we take the previous value of the weights, theta, and we take the current value of the weight, and then we do a additional term, which is usually negative, where we have the learning rate multiplying the gradient, which is this expression over here. Okay, so anyway, you got to have that idea in your mind, that machine learning is all about gradient descent or stochastic gradient descent, and it's all about adjusting the weights. And although the weights could have been adjusted using a closed form solution, we don't do that because of computational issues. We go into an iterative algorithm, which is gradient descent. And so the error function also takes the form of a regularized error function. So in this case, E of W, what is the amount of error or loss encountered with W, is 1 due to the data ED of W. And the other one is EW of W, which is the weight associated with a particular W that you've chosen with a lambda multiplying it. And we refer to this term, it's a peculiar term. It's called a Lagrangian term. This comes about when one is trying to minimize two things at the same time. You want to minimize the sum of squared errors on the one hand, and you want to minimize the length of the weight vector at the same time. We talked about this last time. Length of the weight vector, we want to keep it minimum, otherwise it's going to be a case of overfit. It's trying to run through in a very detailed way all your data. We don't want that. And so this is again the machine learning contribution. Machine learning has introduced this idea of regularization, we call it. This is called the regularization term that we add on, and we say this is the quantity you need to minimize. All right. And so when we have a simple form of the regularization term is half of W transpose W, that is the length of the weight vector, then the total error term has this form. This regular is called weight decay also, because in sequential learning, weight values decay towards zero unless supported by data. All right, so this is weight decay. So if you want to keep this minimum, it means W should become smaller and smaller, it should go to zero. And that's why it's called weight decay. We're making it smaller, but the data is what keeps it away from zero. You say you need a W that's really the appropriate one for this data. So it's kind of an interesting interplay. Uh, the error function remains a quadratic function of W. Interestingly, if this is what you're going to be doing, this has a closed form solution. Previously, our solution was EW was the sum of squared errors. And that is what led to a closed form solution that says, what is a W is nothing but in terms of the design matrix and so on. What if we add this, what happens to it? Well, that also leads to a closed form solution. And that expression W has this form, this equation in the middle of the slide. W equal to lambda I plus phi transpose phi inverse phi t. All it is if you're going to be using a weight decay regularizer, then the form of the closed form solution is this one. And how does that differ from the previous one? The previous one was this. WML was this expression. This whole thing, this whole messy thing here in the beginning was the Moore-Penrose inverse. This one has the Moore-Penrose inverse appearing in some form, but it also has got lambda I. I is the identity matrix, and lambda is just some constant which is giving the weight you're going to associate with the regularizer. And so it has, this is a closed form solution. This says, okay, no fears. Just take the design matrix and compute this expression in one shot in NumPy, and you're going to have your answer. That's the closed form solution. And so we're going to be saying, well, even there, we don't want this. We want the iterative solution. So it's kind of interesting to look at the geometric interpretation of regularization. This picture here is showing you how a bowl like this is what's called as a convex function here. There's a convex loss function or error function. And this is a two-dimensional cross-section of this bowl here. So we got all these contours here. It's got the outermost contour is somewhere way up high here. And then the inner and inner and inner contours that's going down and down and down to the minimum of this loss function here is at the bottom, saying that's where the loss function is going to be smallest. And that's what we are looking for. What should be the value of W1 and W2? So we are at right in the middle of it. And that's what the sum of squared errors loss looks like this. And we are looking at a two-dimensional cross-section of it. And this is a three-dimensional version of that loss function where W consists of W1, W2, W3. And but if we regularize it, we're saying that don't give me an answer that says the answer is W1 and W2 correspond to the center value. This says I want a solution that not only keep this quantity, this bowl small, but I also want to keep the length of that weight vector as small as possible. So length of the weight vector is measured from the origin here to the center. And so we say, okay, that's somewhat of a high value. Maybe you should give me a smaller value of W. Then we say, pull it back towards the origin. This is weight decay. Pull it back all the way to zero. That's what that half W transpose W is telling you. So we have both of these constraints. One telling you go closer and closer to the bottom of this bowl. The other one is telling you go closer and closer to the origin. So how do we reconcile these two? And that is the beauty of this idea called Lagrangian. which says your error function now has the sum of squared errors plus lambda over 2w transpose w. Lambda tells you how important is this term. If you make it very large, that's very important. If you make it 0, it's not at all important. And if it is a small number, it is somewhat important. So you're going to make a compromise between being in the center of this and being close to the origin. So the compromise depends on your lambda you chose, and it might push it to this point here. You see all the points along the contour have the same value there. It could be any of those values will give you the same error. And we want the value closest to the origin. So it's okay, it says find something closest, depending on the lambda. So it's going to be somewhere along this vector joining the center to the origin, and we'll find some point in between. And that is the geometry of regularization. So this is again shown here. We've got W2 and W1, and we have so many values of W. Blue are the contours of unregularized error function. That's this bowl. In this case, the center is sitting over here. And then we have this is the contour with a quadratic regularizer, W transpose W. And so we are saying that has to be weighted. And so the compromise between the two. So we are trying to find the smallest value, W star, that minimizes this quantity and also keeps it as close to the center as possible. If it chosen any point somewhere else, that would make it that would have the same distance to the origin, but it would make it further away from the center here. So W star is the solution, is the one that is the regularized solution to the problem. So a more general regularizer, other than using the square of the Euclidean norm, we say, of W, you can state a general version of it where Wj, this is the absolute value to the power of Q, where Q equal to 2 corresponds to the quadratic regularizer. All right. And if you choose Q equal to 1, which is not quite the square, but sum of all these values, Q equal to 1 is known as a lasso. So you see in the machine learning literature that other people will say that I used a quadratic regularizer, or we used a lasso regularizer. Lasso has the property that if lambda is sufficiently large, some of the coefficients of Wj are driven to 0, leading to a sparse model in which corresponding basis functions play no role. So some of the, if lambda is sufficiently large, and so some of the coefficients are driven to, so there are certain properties here. Let's see. It's kind of interesting. What is the generalization of the idea of a circle for different powers that you use? A circle uses a square, right? Wj squared we'd have. So that's a quadratic. We'd say W1 squared plus W2 squared equal to constant. That is the locus of this green points, the circle here. So that is the equidistant points. But if you use Q equal to 1, points along these diagonal lines, they're all equidistant from the origin. It's only, it's the idea of the block distance, right? When we say 2 blocks or 1 block, right? So it's 1 block away, 1 block away, 1 block away, 1 block away, I suppose. And I guess this would all be thought of as 1 block away. Okay. You could even choose Q equal to 0.5. We have W1 square root W2. You get so this is called a circle in this world. A circle in this world of Q equal to 0.5 looks like this. A circle in the world of block distance looks like this. A circle in our Euclidean distance looks like a real circle. And what if we chose Q equal to 4? It's kind of peculiar. It's kind of interesting shape here. So you see, you can create all these shapes by you choosing different powers of Q. And why is this relevant to machine learning? Is machine learning mostly uses this Euclidean version, but sometimes they use Lasso. It's called quadratic and Lasso. The others, interesting to play around with. This is an explanation of why do you get sparsity with Lasso constraint. I don't know. We could try and understand what this is saying. Might be interesting if you like the geometric interpretation. Um, so it says with q equal to 1 and lambda sufficiently large, some of the coefficients wj are driven to 0, leads to a sparse model where corresponding basis functions play no role. And origin of sparsity is illustrated. Why does it become sparse? This is the quadratic solution we saw where W1 star and W0 star are non-zero. Right. So we have a solution here. W1 star is non-zero. W0 star is non-zero. A minimization with a Lasso regularizer, a sparse solution with W1 star equal to 0. So this is this particular weight associated W1 is 0 because your solution is ending up here, right on top of this. And so we say this is a sparse solution in that one of those features doesn't matter at all. W1 does not matter. You're going to be associating 0 with it in your solution that you're going to end up with. You remember regression is about finding the weights for all your input features. If you're going to associate 0 with an input feature, you're saying that feature does not matter in making my decision. Well, that's pretty serious, isn't it? So we're throwing away some information that was produced by the camera or whatever input device you had, saying, I don't need that. We only work with the others. That's what a Lasso regularizer is going to do. The advantage of a sparse solution is computationally it becomes easier to deal with. You can throw away lots of numbers from your features, work with a smaller set, and advantages. A sparse solution, it's an approximate solution, but you don't have to compute as much as needed, but you might not get a very accurate solution. So the conclusion of this side of this part of regularization is that it allows complex models to be trained on small data sets without severe overfitting. All right, and it limits model complexity, how many basis functions to use, and problems of limiting complexity is shifted to one of determining suitable value of regularizing coefficient. Okay, so regularization is a big topic. It is about generalization. We didn't even mention that in this slide, but it solves these practical issues of controlling the complexity, driving some of the weights to 0, or to allow us to do something with whatever data that's available using some other constraint other than the data constraint. So summarizing linear regression, it consists of I just threw in all the equations you need. So it might kind of be a little bewildering to you when you're new to machine learning, but it's really something, you can get a mastery over these equations. Y of x comma w, the output y of x and w is written as a summation over phi j. These are the basis functions. So I can write it as w transpose phi of x, where you have m basis functions, right? And an example of phi j of x, what is this phi j of x? It could be a Gaussian basis function. This is very much like a multivariate normal distribution. An objective function without a regular objective function, or the loss function without regularization, looks like this. So it's Tn minus W transpose phi n of x squared. Or when you bring in the regularizer, it's going to have this form. And then the closed form machine learning, not machine learning, maximum likelihood solution is this without regularizer. With regularizer has an additional term here. And what is this phi again? Is this design matrix. And the gradient descent is Wt plus 1 equal Wt minus eta. And then the derivative of the gradient is what you need, because that's, it says I need a derivative, delta or whatever this is, del En. Del En has this form where the square is gone and in the half is gone and the square is gone, but then we have a phi of x multiplying it. And when you have a regularizer, the derivative is a slightly different form where you have a plus lambda w here. Okay, so that is linear regression with basis functions and regularizer. Okay.
Professor, there's
Yeah.
one question by
Yeah.
Vineet. So his question is, why must the squared sum of weights be less than the learning rate?
Oh, why does the sum of squared errors be less than this? Is that
So,
true here?
so the question is, why is the squared sum of weights be less than the learning rate?
Why is the squared sum of weights? Well, I think you are referring to this W transpose W term, right?
Yes, I
And
guess yes.
right?
Hi,
Uh,
this. So I actually saw that a couple of slides ago, like in slide 45 or 46. It said that the squared sum of weights is less than equal to the learning rate. When you were optimizing it, when we were talking about lambda.
See, there are two hyperparameters here now. One is this lambda here, and then there's this is eta. Yes, these are the Greek symbols. We got to pronounce it. We got to name them properly. I call this as eta, is the learning rate. This is lambda, which is the importance of the regularizer. Okay, so those are two terms here. So lambda is a quantity that I think we saw some slides of this last time. What happens? Oh, we saw maybe for the learning rate we saw, and what happens when you choose different values for this eta. We can do a similar thing with lambda, and we can do some experiments to choose an appropriate form, which is good for the particular problem. We don't have these are hyperparameters. Yes, eta and lambda are hyperparameters. They are not like the regular parameters W. Those are all learned from the data. These are something that's somehow fixed by the machine learning programmer saying you use this value 0.1 or 0.2 or something like that here. Then the question comes in, how do I fix that? So for that, you can run some experiments with different settings and see at what point you're going to have, we can use holdout method and so on, and that becomes part of your training also to figure out what choice leads you to the best solution. Okay, does that answer your question? So it has nothing
But
to do with the W's and the lambdas are independent operations.
yeah, partly it does. What I saw there was that the choice of W's or the values of W should not go larger because of lambda. So lambda is penalizing them, and the values of
Let's
W
go
are
to that
obviously
slide
getting
you're
small.
talking about. Are you referring to one of these slides?
Yeah, can you go back one
Maybe
slide?
this one. Yeah.
46 or 45.
All
Yeah.
right.
Okay. In regularized case, choose that value W subject to the constraint. Yeah, that part.
You're asking why shouldn't this W become larger? That's what you're asking the question, right?
Yeah, like why is the sum less than a learning rate? As I think the learning rates are
Oh,
already
this
very
one here,
small.
this equation here.
Yes, correct. Yep.
Uh, so it's subject to some constraint. There's a bit of confusion here happening. This eta is the learning rate. That's what you're saying, right?
Yeah, that's what my understanding is.
Oh,
Eta is
I see. I
located
see.
within.
That's a valid question you're asking me. Where does this eta come into play? Um, so that has just come out of the blue at this point there. Okay, I'm just ignoring that particular expression here. We are just looking at this term. This
Okay,
is
yeah,
what we are
the
trying
bottom
to
one is.
minimize. In
Yeah,
which
the
case,
bottom
this
one
is
is.
being ignored. And I'm afraid this might have come in as a different constraint here. All right. So we're I didn't in my explanation did not include that equation at all. That this inequality at all. And is that eta the same eta as the learning rate, which is something that we're ignoring. Okay. All right. Mayor, you want to add anything to that?
No, Professor.
Yeah. Okay. Fine. Fine. All right. That's a very good question you asked. So just ignore this inequality here. There's really no relationship between the eta, the learning rate, and this. We're simply trying to minimize this quantity here. I need to look it up. Where did I get that from? So, Chris Bishop's book might have that. You may want to do that too. Is that a valid inequality? That's also we're trying to do. I guess not really. Okay. So yeah, some of these material is from Chris Bishop's book on machine learning. Okay. Yeah. All right then. Good question. Shall we move on then?
Uh, so there's
Yeah.
one
Yeah.
question
Go
by
ahead. Go ahead.
Daniel.
I like the questions. Go ahead.
So there's one question by Daniel. This question is there a prescribed way that basis function yield a scalar value from a given input vector? For example, the function phi j that you had in the summary slide in the upper right
Oh,
corner.
summary slide. Okay. Let's go to the summary slide. Yeah.
So the phi j function that you have on the upper right corner, is this like a prescribed way of calculating a scalar from a vector input?
Very good question. You know, there are some basis functions that are popular, commonly used. So this is exactly correct what you're saying. We're taking an input which is a vector x, which could be an image from your camera, and that is being mapped. What is this? This whole thing is a scalar quantity. Like a Gaussian distribution, when you plug in an input, the Gaussian distribution gives you a value of a probability density function. You can think of it as a probability. It's a probability density function. It's a scalar value, some number, real number. So this is a real number here that is being calculated here. So your question is there, what kind of scalar functions can we use? This is what's called as a radial basis function. It's kind of centered around some mu j, some mean, and it spreads around that like a Gaussian hill, right? So you're kind of saying as you move away from that point, it has got less importance. So this is the jth basis function. Each basis function has its own mean mu j, and the spread of it is controlled by this sigma here. So we have a set of basis functions, m basis functions. We specify m points in that space, and that is so that's a Gaussian basis function, a radial basis function. Radial basis function, why do we use this particular form? Is it has got a cognitive basis. This is how the human eye, for example, when we fixate on a point in space with our eye, I mean, our eye is not getting a very clean, same resolution picture of the entire whatever you're looking at. It's fixating on some point, and that point you're going to see it sharp, and all the points around it as you go away from that fixation are seeing in a blurred and blurred and blurred way. So it kind of is behaving like a radial basis function of a cognitive sensory mechanism, and that also works well with the data. There are also a few others you see occasionally, like wavelets and so on. They use slightly different types of basis functions. So, I think I gave examples of basis functions, like even sigmoid can be used as a basis function and so on. But, which is better and all this, these are all kind of interesting research questions. And you always, in neural networks, machine learning, we favor solutions that are biological like. All right. So this is a biological type like basis function. Okay. Did that answer your question?
Uh, Not entirely. It was my
Okay,
question
ask
is
again.
it's very much just the math involved. And the example I would give you is in that phi j function, there is the x minus mu j subtraction, and we performed that in the breakout activity, and it yielded a vector that we performed element wise subtraction, and then we had to sum all the elements of that vector together. And it was just sort of an implicit or implied operation. And I've myself found it confusing. So
So
when I
you were
see it,
trying to implement it from scratch, x minus mu j transpose times invert the covariance matrix and that kind of thing, right? That's where you are running into issues. Yeah. But the whole expression is nothing but a standard Gaussian distribution with mean mu j. All right. So you're asking more about the actual computation of that which you're trying to do and running into issues there. But anyway, look at it at what is it trying to do is what I'm trying to answer. You're saying how is it being done is your question. Yeah.
yeah.
Mihir, you want to take that up? You've seen the implementations.
Yes. So I guess the question is valid. You have an implicit summation sign when you are calculating x minus mu j, and that's not showcased here. It's only the resultant of x minus mu j which has to be transposed and then multiplied with the inverse of the covariance matrix. But one thing to note here is that the phi j that you're getting here is just the scalar value for just one basis function. So you'll have phi1, phi2, phi3, so you'll get three scalar values. And here it's just a representation of how you convert a vector of input to a scalar value.
Okay, good answer, Mihir. Okay, good question and valid question, I should say, on the computation that's going on. All right, Daniel. No?
Yes. Thank you so much.
Okay. Okay. All right. Yeah. It's good. I enjoy getting your questions on these things because it wakes up everybody saying what is going on. Otherwise, I'm just going blah, 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 and nobody's getting anything out of it. Yeah. All right, then. Let's see. How are we doing? Should I begin the gradient descent part or should we? All right. We have 6:15. So Mihir, we can go for another 10 minutes, right?
Yep, another 5 to 10 minutes.
5 to 10 minutes. Okay. All right. Okay, do you see the slides titled Gradient Descent? Good.
Yes,
Do you
Professor.
see it? No?
Yes, Professor.
You're seeing gradient descent. Okay. All right. This is just a continuation of that large set of slides, which was linear regression with basis functions. And there's a little bit more on in some nitty-gritty details, I would say. Simple gradient descent ascent. We prefer the descent. SGD is what we call it. We don't call it SGA. If it is a positive value, we are trying to maximize. We take it into a negative value and minimize it. So maximum likelihood becomes descent when we make it negative log likelihood. And then difficulties with simple gradient descent. Okay, so simple gradient SGD is not the answer always. And there are some improved methods called line search, Brent's method, conjugate gradient descent, weight vectors to minimize error, and stochastic gradient descent. All these topics are there. What it is saying is when you are implementing a machine learning program, you are faced with some choices. So, would you like to use simple gradient descent or Would you like to use a line search method? These are all methods for narrowing down the, like for example, if you chose your eta to be very small, it might take a long time. If it is very large, it might over skip, so on. So they come up with some solutions to these problems. So you encounter it when you want to say, I need to choose this properly. So all right, let's see what this says. Gradient-based optimization. Most machine learning algorithms involve optimization, minimize, maximize a function by altering the what we're trying to minimize or maximize, usually stated as a minimization problem. Maximization accomplished by minimizing minus f of x. All right, so it's descent. F of x is referred to as an objective or criterion. So many words used. It could be objective function, criterion function, loss function, error function. In minimization, also referred to as loss function, cost, or error. So it's a bit confusing, but all of these are kind of interchangeable terms as long as we know what we're talking about. And example is linear least squares. So we're using some kind of a function here of x, some matrix times x is compared to a b, which is the targets, and we make that as small as possible. And we denote the optimum value by x star is equal to arg min f of x. So that is what value of x is going to make that as small as possible. So calculus and yeah, this is a little bit more explanation of why we're doing this. This is only if you are curious enough. Consider a function y equal to f of x, x and y real numbers. Derivative of function denoted f prime of x or as dy by dx. And derivative f prime of x gives the slope of f of x at point x. So it's reminding you of the calculus origins here. It specifies how to scale a small change in input to obtain a corresponding change in the output. So f of x plus epsilon is equal to approximately equal to f of x plus epsilon times f prime of x. And it tells you how to make a small change in the input to make a small improvement in y. We know that f of x minus epsilon times sine of f prime of x is less than f of x for small epsilon. Thus, we can reduce f of x by moving in small steps with opposite sign of derivatives. So it is trying to answer that question again as to why we are taking a negative when we are updating the weights. So it goes back to gradient descent of Cauchy, 1847, right? And I don't know if I went over this again. And when we're trying to minimize this blue function, which is 1/2 of x squared, if we're on the right side, we decrease the value because the f prime of x is positive. If you're on the left side, f prime of x is negative. So we add things by moving this direction. Ideally, we want to move to a point where this 1/2 of x squared is as low as possible. It's lowest when x is equal to 0. It's got a minimum. We're trying to find that minimum. So this kind of illustrates gradient descent. Point that I think I might have mentioned already. Minimizing with multiple inputs, same kind of behavior. This again shows you, I was trying to explain the idea of multi-dimensions, same idea we saw. Keep in mind that whenever I write this del E W, W is a vector, this is also a vector. Del E, these are all partial derivatives with respect to W naught, W1, Wn. So this is called a partial derivative. And that's what's being said whenever we use del of EW. It's this vector consisting of all the partial derivatives. And directional derivative is the direction comes into play when you're trying to, because after all, we're proceeding in some direction, saying which direction is going to minimize this. So anyway, I leave it for you to look at that kind of detail. And the gradient descent rule is again, W gets W plus derivative W, and that this delta W is a minus eta times derivative EW. And so this is what's going on. Again, the repetition of some of the ideas. And the steepest descent proposes a new point. And these are the equations. Machine learning is full of equations, right? So you need to get comfortable with these equations. Those are your friends. Your equations are your friends. And all the others is all wording to trying to explain what's going on. So this is showing you the idea of a simple gradient descent. We go from A to, this is the simple gradient descent procedure of theta t plus 1 gets theta t minus thing, t plus 1, while this is greater than or equal to delta, you return. So as you know, as long as there's a very small change that's going on, then you stop. So this is what's going on in simple gradient descent. And this is showing you how it works with gradient descent with least squares. Then there are all these other issues where there are what are called saddle points, maximum points, saddle points, and so on, minimum, maxima. This is a minimum function, maximum function, it's a saddle point function. And there can be multiple minima. I think one of you asked the question earlier on today saying, why don't we use genetic algorithms where this minima problem is not there? In deep learning, we simply plow ahead and use these methods, stochastic gradient descent, even though we don't end up at a global minimum like this. Here is the global minimum. This is a local minimum. We end up at a local minimum, and we say that's good enough. That works pretty well. So deep learning seems to work pretty well using, not necessarily finding the globe. You follow gradient descent and you end up here. Because if you started here, you go this way. If you start here, you go this way. You'll never jump out of it. Whereas other algorithms trying to say, no, I must be finding the global one. So maybe genetic algorithms has a solution to it, and that might be an answer. But machine learning uses stochastic gradient descent almost universally. And here are the difficulties with simple gradient descent, that there is overshooting or extremely slow. This is overshooting method. It is jumping like that. Whereas the other one is going slowly like this. So we want to avoid. So convergence of deepest design. So there are some solutions. Line search is a method, and set eta to a small constant. Another person, line search, evaluate for several values and choose the value that results in the smallest objective function value. So line search is a particular approach that says, try out a couple of values. I think this is what line search is. It says, try out a couple of values, figure it out at eta 1 what's happening, figuring out what is happening at eta 2, and then you find a point somewhere in the middle, choose eta prime, and use a binary search. So we say that eta prime is, so we need to find 3 points, I suppose, eta 1, eta 2, eta 3, and we find something in between such that it's eta 1 plus eta 3 divided by 2. So it's like some kind of binary search. You're trying to find something. It says, find this point here, find this point here. And once you have found those 2 points, you get a value in between the two. So that's kind of bracketing 2 sides. So in binary search, that's what we do. We kind of know it's higher than that or lower than this, then jump in the middle, that kind of thing. So same thing can be done for determining eta. So it's giving you a nice heuristic approach. There is another variant faster than line search called Brent's method. It uses a quadratic function, which is approximating this true behavior of the loss function with respect to eta by a quadratic function. It's faster, so on. And then there is a version called conjugate gradient descent, which says instead of jumping like this through the contour, wasting a lot of time, is it possible to kind of jump to a point very close by? And so that's called conjugate gradient descent. There's a bit of mathematics involved here. It says, remember the past directions and bias in new directions as a combination of current G and the past H. So it is some clever method. that remembers where how you're going, although you're skipping like this and like that and like that and like that. So, okay, you're kind of proceeding along here. Then let's continue along the trajectory and jump all the way and see what we need to do. That's pretty clever. Progress is zigzag, and that zigzag is kind of eliminated.
Sorry to interrupt, Professor.
Yeah.
It's 6:25. Can we start with the quiz now?
Okay, you want to start? Okay, fine. All right, I was going to stop anyway. So anyway, this type of style, there is all kinds of little detail people have worked on. Not everything we want to go over. We want to get a big picture here, and a lot of it today are available as library functions, Brent's method or line search and so on. Okay. All right, I'm going to stop here, and I'm going to make Mihir the host so he can carry on with what he plans to do.